In module 5 of chapter 9, we shall learn about the asymptotic directions and asymptotic lines. Secondly, a theorem, that is Euler's theorem on normal curvature, and thirdly, Dupin integratrix. Now, what is asymptotic lines? When normal curvature of a surface vanishes, then the directions are called asymptotic directions, and the curve whose tangent at each point is directed along the asymptotic directions is called asymptotic line. So, in this module we shall learn about these things, and we shall see that when the parametric curves or the coordinate curves are the asymptotic curves, and we shall also try to find some examples and the equations for asymptotic lines. Nextly, we have also see the Euler's theorem on normal curvature, and lastly the Dupin integratrix, which indicates the nature of a surface, whether the surface is elliptic or parabolic or hyperbolic. So, let us start chapter 9, module 5. Now, in module 5 of chapter 9, we have the learning objects like this. The first one is asymptotic lines, second one Euler's theorem on normal curvature, the third one Dupin integratrix. Now, let us start with asymptotic lines. The directions on the surface given by kappa n, that is the normal curvature, and we know that normal curvature is equal to b alpha beta lambda beta equals to 0 are called asymptotic directions. Just I have mentioned that if the normal curvature on a surface vanishes, then the directions are called asymptotic directions. So, kappa n equals to 0 gives us the asymptotic directions, and the curves whose tangents are asymptotic directions are called the asymptotic lines of the surface. Now, the asymptotic directions are real and distinct when the Gaussian curvature, this k is the Gaussian curvature, is less than 0, imaginary when Gaussian curvature is greater than 0, and identical when Gaussian curvature equals to 0. Now, let us see an example that a straight line on a surface is an asymptotic line. Now, as the curve is a straight line, its curvature is 0, kappa is 0, and hence we have b alpha beta lambda beta equals to 0. Thus, the straight line is an asymptotic line. So, it is very obvious example that the straight lines on a surface are the asymptotic lines. Now, let us see that when the parametric curves are asymptotic lines, and we have this condition that the parametric curves are asymptotic lines if and only if b11 equals to b22 equals to 0. So, this is the condition for the parametric curves to be asymptotic lines. Now, let us see how it is coming. Now, first we consider that the parametric curves are asymptotic lines. Then we have B alpha beta lambda beta equals to 0. This is the condition for the asymptotic lines. Now, for U1 curve, we have B alpha beta lambda 1 alpha lambda 1 beta equals to 0. So, we have B 11 by A 11 equals to 0. If we just break this one, we are getting B 11 by A 11 equals to 0. That is B 11 equals to 0. For U2 curve, similarly, we get B alpha beta lambda alpha 2, that means for U2 curve lambda beta 2 equals to 0, and we have B 22 by A 22 equals to 0, and for the first fundamental form to be exist, A 11 A 22 should not be equal to 0. So, we have B 22 equals to 0. So, we got the condition that when the parametric curves are the asymptotic curves or asymptotic lines. Now, conversely, let B 11 equals to B 22 equals to 0, then they will give B 12 D 1 D 2 equals to 0. That means D 1 D 2 equals to 0. Now, as B 12 is not equal to 0, therefore, the curves are parametric curves, because if we just take D 1 equals to 0, then we are getting U 1 curves, and D 2 equals to 0 gives U 2 curves. Now, let us see next problem, that find the values of H and K, where H is the mean curvature for the surface, what we have earlier discussed, and K is the Gaussian curvature of the surface. So, find the values of H and K when parametric curves are asymptotic lines. So, when the coordinate curves or parametric curves are asymptotic lines, then we shall find the mean curvature of the surface and the Gaussian curvature of the surface. So, let us see the solution for this problem. Now, Gaussian curvature is equal to B by A. From the Gauss equation, we got this condition that Gaussian curvature equals to B by A, where B is the determinant of B alpha beta. B alpha beta are the coefficients of the second fundamental form, but when the parametric curves are asymptotic lines, we just got that B 11 B 22 equals to 0. So, this B becomes only minus B 12 square by A. So, Gaussian curvature becomes only minus B 12 square by A. The mean curvature, we know that mean curvature is defined as half A upper alpha beta B alpha beta, where A upper alpha beta is the reciprocal tensor of the first coefficient of the first fundamental form. So, if we just break the expression and using B 11 B 22 equals to 0, we get H equals to minus A 12 B 12 by A. Now, let us see the asymptotic lines for this conoid given by the equation r equals to u cos v, u sin v, f v. We are going to find the asymptotic lines for this surface. Now, we can easily find these values because earlier we have obtained these values. So, you can easily find this B11 equals to 0, B12 equals to minus f1 by root over u square plus f1 square, B22 equals to u f11 by root over u square plus f1 square, where obviously f1 is df dv and f11 is d2f by dv2. That is the second order derivative of the function fb is represented by f11 and the first order derivative is represented by f1. f1 is equal to df dv. So, we can easily find the xi. Xi is 1 by root over u square plus f1 square, f1 sin v minus f1 cos v comma u. Thus, the asymptotic lines can be obtained by this equation. If we put in the condition for asymptotic lines, we get the equation of the asymptotic lines is this minus 2 f1 du dv plus u f11 dv square equals to 0, as root over u square plus f1 square is greater than 0, or this one can be written as in this form. So, from here we get either dv equals to 0, that means v equal to c1, c1 being constant, or minus 2 f1 du plus u f11 dv equals to 0. So, from here we get minus 2 du by u plus f11 by f1 dv equals to 0. Now, solving or rather integrating, we get this one minus 2 log u plus log f1 equals to constant, or we can write this one minus log u square plus log f1 equals to constant, or you can express this one in this form log f1 by u square equals to constant. Therefore, f1 equals to c2 u square, or u2 equals to d1 f1, where d1 is written as 1 by c2 and v equals to c1. So, these are the asymptotic lines for the surface conoid given by the equation just expressed in the previously. Now, in section 2 of module 5 of chapter 9, we shall learn a theorem called Euler's theorem on normal curvature, which relates the lines of curvature, the normal curvature and the principal curvatures also. And nextly, we shall learn about the Dupin integratics. Dupin integratics is the system by which we can characterize the nature of the surface, and at that point on the surface we can make a conic section which also characterize the nature of the surface at that point. So, let us start the Euler's theorem on normal curvature. So, let us see the statement of Euler's theorem on normal curvature. If the lines of curvature are not indeterminate at a given point on a surface, and if alpha is the angle between a given direction and a principal direction at that point, then the normal curvature kappa n can be expressed as in this form, kappa n equals to kappa 1 cos square alpha plus kappa 2 sin square alpha. So, this kappa 1 and kappa 2 are the principal curvatures of the surface, and kappa n is the normal curvature of the surface. So, this theorem relates the lines of curvature, the normal curvature and the principal curvatures. So, let us see the proof of this theorem. Firstly, we assume that the given point is not an umbilic point. So, if the parametric curves are considered as the line of curvature, then the principal curvatures at that point are kappa 1 equals to B 11 by A 11 and kappa 2 equals to B 22 by A 22. In our previous modules, we have learnt about these things, that if the parametric curves are the principal curvatures, then the values of that principal curvatures, that means along U1 curves and along U2 curves, we have these expressions kappa 1 equals to B 11 by A 11 and kappa 2 equals to B 22 by A 22. Now, let alpha be the angle between a given direction dV1 dV2, these are the components of the direction, and a principal direction at the given point. Now, since A12 equals to 0, the parametric curves are orthogonal. So, the expression for cos alpha will be equals to A11 dV1 by ds dV1 by ds, and from the first fundamental form we have the expression dV1 by ds equals to 1 by root A 11. Thus, cos alpha equals to A11 dV1 by ds 1 by root A11, that means root A11 dV1 by ds, and cos pi by 2 minus alpha, that is equal to sin alpha, equals to root A22 dV2 by ds. Now, as the parametric curves are taken as line of curvatures, so the normal curvature at that point is kappa n equals to B11 dV1 square plus B22 dV2 square by ds square. Now, we know that the normal curvature kappa n is equal to the second fundamental form by first fundamental form. That means, kappa n equals to B alpha beta du alpha du beta by A alpha beta du alpha du beta, and we know that A alpha beta du alpha du beta can be expressed as ds square. So, kappa n is coming to this form, and then the right hand side becomes B11 dV1 by ds whole square plus B22 dV2 by ds whole square. So, this becomes B11 by A11 cos square alpha plus B22 by A22 sin square alpha. Now, we have just seen that when the parametric curves, the principal curvatures are B11 by A11 and B22 by A22. So, kappa n equals to kappa 1 cos square alpha plus kappa 2 sin square alpha. So, note that the Misner's theorem and this Euler's theorem give the complete information on the curvature of any curve on a surface. So, these are the two pillars of the surface geometry, and for any curve on a surface we get the complete information about that curve on that surface by these two theorems, Misner's theorem and this Euler's theorem. Now, let us see the Dupin indicatrix. Now, this is the definition for the Dupin indicatrix. The intersection of a surface and a plane parallel to the tangent plane to the surface at some point and near the tangent plane is approximately a conic section which is similar to the indicatrix fixed at that point. That means, by looking into that conic section, we can see the nature of the point on the surface. That is, if on the surface at the point P the Gaussian curvature is greater than 0, the point is elliptic, and so the Dupin indicatrix will be an ellipse. So, just getting this the conic section, the nature of the point on the surface can be determined. If the Gaussian curvature is less than 0, the point is hyperbolic, and so Dupin indicatrix is a hyperbola. And for k equals to 0, the point is parabolic, and so Dupin indicatrix is a parabola. Now, these things can be visualized by the given figures here. So, now let us see this figure from where we can see the Dupin indicatrix. Now, from the first figure we see that P is an elliptic point, the surface is like a egg-shaped surface, that is an elliptic surface, where the Gaussian curvature is greater than 0. For the second surface, it is a parabolic surface and the P is a parabolic point, and here the Gaussian curvature is equal to 0. That means, here if we take a section we get a parabola, and for the first figure if we take a section we will get an ellipse. Now, in third figure we see that this surface is a hyperbolic surface and the point P is a hyperbolic point, and here the Dupin indicatrix will be a hyperbola. So, from these three figures we can see or visualize the Dupin indicatrix. So, in module 5 of chapter 9, we have learned three things. The first one is asymptotic lines, second one Euler's theorem on normal curvature, and the third one is Dupin indicatrix. From asymptotic lines we have seen the condition that when the parametric curves are asymptotic lines. We have seen some examples also and obtained the asymptotic lines for a surface called conoid. In Euler's theorem, we have seen the relation between the normal curvature on the surface and the principal curvatures of the surface. And lastly, we have seen the Dupin integratics, where the conic sections can be the main part, where the nature of the point of a surface can be determined, that whether the point is elliptic point or hyperbolic point or parabolic point, we can visualize them by nature of the conic sections, which is known as Dupin integratics. So, with these three things we end this module.